the first talk of the afternoon, it gives me a lot of pleasure to introduce Yongdae Kim. Yongdae joins us from KAIST, the Korea Advanced Institute of Science and Technology, where he's a professor in the Department of Electrical Engineering and also in the Graduate School of Information Security. He currently serves as the head of the Police Science and Technology Research Center at KAIST and previously directed the Cybersecurity Research Center. Yongdae's research group is among the leading users of srsRAN around the world for mobile wireless security research, with leading work in the fields of physical signal overshadowing, cellular location tracking, Simbox fraud prevention, and LTE sniffing. He regularly serves as a program committee member for top security conferences, including IEEE S&P, ACM CCS, too long, cut to the chase, nearly finished, Usenix Security and ISOC NDSS, and I'm delighted to introduce Yongdae.
All right, thank you. All right. So this is my great pleasure to give a talk here because I'm the biggest fan of the srsRAN. So anyway, so I'll be talking about my experience of using SRS, and I'll also invite my students to give him opportunity to experience a talk in front of these experts. Anyway, so in the last 11, 12 years, I've been publishing about 14 papers in mostly top conferences. And my first actual cellular paper started from 2012. And that paper is showing that was actually the first paper showing that you can check if some user is in the some cell or not. And so in the last in the last 12 years, I've been working on this problem, but because the title, so this is actually a better view. And so as Roger, where is Roger? Roger explained, I'm the guy who has been publishing new vulnerabilities and attacks, not fixing it. We talked about location and identity leaks in NDSS 12 and 18, and we found some accounting bypass in NDSS 14 and EuroSMP, and signal overshadowing attack. I will talk about it a little bit later using security 19, and we show that you can actually fingerprint some particular user watching particular video, even though it is encrypted by exploiting the MAC layer. And also, we recently released LTE sniffer, which is the uplink downlink sniffer at YSEC 23. So those are kind of new vulnerabilities and attack papers. And then started from VLTE in 2015, we've been publishing many papers about testing cellular infrastructure such as VoLTE and performance bugs or uplink or downlink fuzzing of the core network or basebands, or stateful downlink fuzzer, as well as the UE fingerprinting to find out if whether you can fingerprint the UE. And also we did some static analysis of the baseband as well. So yeah, I mean, I've been everywhere, right? And because this is a SRS workshop, we should be talking about the platform we were using in 2012. And this was actually what Roger mentioned. So we were using that particular, the famous Osmocom BB running on a PC. And at that time, because there is no radio, when you buy Motorola C118, then the audio cable and connect it with the USB, and you can actually bypass the baseband of the cell phone. And the software inside the PC is actually replacing that Osmocom is actually the software radio. And there is that the particular cable was, we needed that particular cable at that time. And so there was, when you sniff 2G, this was the tool in 2012, right? Since 2000, I mean, around 2015, there are a lot of cellular security papers coming out. And I think the biggest change we have in the last 7 years is actually we have a new threat models. So we talk about fake base stations, fake UEs, and sniffers, and man-in-the-middle attack and overshadowing attacker. I mean, all those attack models have been discussed in theory, but without SRS, such srsRAN, such implementation was not possible. And this has been materialized with these softwares. I mean, we can implement a fake base station using srsc node B or srsc PC. And for fake UE, you can implement with srs UE. And sniffer, now you should download LTE sniffer because the open aeoscope sold by SRS is too expensive. This is free, right? And MITM attacker, I have not seen anyone actually professionally implemented MITM attacker professionally. But in theory, you should be able to implement using srsc node B, srsc PC combined with srs UE. And the overshadowing attacker is what we implemented in Silver. So interestingly, right, these attack models have been implemented by us and using SRS product, right? Then you might ask, why we use SRS, right? So, I mean, this is what I've discussed with my students, and the students give me reasons why we are using SRS instead of others. I mean, of course, the other candidates will open an interface and open LTE. And I asked my students, and they say, oh, srsRAN for LTE experiments is because it's fully compatible with the commercial LTE networks, right? And srsRAN supports more features in different layers, and such as transmission modes, carrier aggregation, and paging, while most other competitors don't. And Voltaire also can be supported with the Chameleon IMS. So in some sense, actually, SRS has almost all the options. So it was actually useful for us to test the other things. And I think the very, very important requirement was actually modular code base. And because it is modular, and students can actually take some parts of it and attach it, make a separate product. And easy to understand and modify what are the actual reasons to use the SRS. Because, and we've been using component-based testing as well as the comprehensive testing using SRS, and it was actually all possible. And also it was easy to connect with the commercial LTE network devices and UEs. And because it's easy to connect with the connect means easy to attack, right? And it's actually, I mean, commercial, yes, I mean, commercial devices was very easy to attack with the SRS code base. Thank you. So I've been talking about some of my experience. So in terms of testing, we've been writing many test papers. I mean, probably the first test paper we implemented was called LTE Fuzz. And the title was actually very, very ambitious. And because we thought that we were the first one to touch the untouchables, because we actually fuzzed the core network existing in the carrier. And at that time, there were 3, so Korean government allowed us to test 3 carriers, and they basically gave us access to their test bed in Korea. So using that, we basically generate something called negative test cases. Negative testing, meaning that we generate violating messages. For example, message without MAC, or message with the wrong MAC, or replayed messages. See if those devices from Nokia or Ericsson or Huawei was accepting those prohibited messages, right? And it was actually downlink and uplink testing as well. And this was actually the first paper. And through this very, very simple testing, we found 50 vulnerabilities out of 50, 36 were 0 days. And many of them were basically, because nobody was checking it. It was actually, I mean, yeah. And then because it was a stateless and pre-authentication messages, so later we thought that, okay, when the cellular protocol is actually stateful and has many, many options, we wanted to add actually more better full testing. So that's called do LTE test, right? Please test LTE, right? Door test. And it's a stateful in-depth downlink only negative fuzzer. So it basically tries to find protocol violation vulnerabilities in the baseband. And here we basically generate test cases. And because all those test cases are negative, meaning that those are prohibited messages, it should be dropped silently by the baseband. But if the baseband does not drop, then some attacks should be possible. So here we actually generate about 2,800 messages, right? And using these 2,800 messages, we actually found probably another 30 or 40 vulnerabilities in different baseband, and students get some bug bounty from different vendors such as Apple, Qualcomm, and different places. And this was not possible without using SLS, right? Because I mean, actually this is the stateful testing, meaning that we have to actually to test to some state, right? We have to actually progress to the particular state, and then you can actually send the, violating messages, right? So I mean, the controlling is actually very, very difficult, right? And it was actually over-the-air testing, and probably it takes like 6 hours to test a single phone, single baseband. So it was actually very, very painful, and we tested about 50 phones. And this was actually very, very difficult. But I mean, this is actually fully open source, and you can test your phone using door test, right? It works really well. Yeah. So these are the couple of examples, and I'll be talking about some of the future work later. So testing was one of the purpose of using SRS, and the other was actually using SRS to show that the attack works. And of course, when we talk about the first attack we implemented was actually fake CMOS, right? Meaning that the device is connected to the network, commercial network, and we run the fake base station. This was fun project, but I mean, Side published this. I mean, the vulnerability was published by Side before us, but actually we were preparing this paper. So, okay, heck, we'll just publish the video. Okay. And then we basically noticed that the broadcast messages sent by the cell tower to UE is never authenticated. And telcos say, oh, we are not going to secure the broadcast message. Then it's just that intuitively, you can think that because the broadcast message is not authenticated, if attacker is really, really smart, it can actually replace particular subframe. And can we replace the particular second subframe so that as if the message is sent by the cell tower? Right? Because the message is not authenticated, we may be able to inject it in the physical layer so that the victim does not notice whether the attacker has been sent the message to. this cost 2 years for one poor master student because the synchronization was actually painful. Right? I mean, students told me, Professor, 5 millisecond off. Then next day, minus 10 millisecond off. And it was like that. I mean, the experiment was like that all the time. But I mean, and actually students read SRS code, and that was actually very helpful because when you read the specification, sometimes you don't understand exactly how it works. But when you read the source code, actually, students have a much better idea about actually how it works. And because of that, they found some ways to actually implement the synchronization correctly. And the attack, I mean, this attack was actually very, very powerful. And yeah, I'll talk about the implication later. But I mean, this is actually a very interesting attack called access barring. I want to skip it, but probably I cannot skip it, so I'll explain it. So it shows that the phone is under, it works normally, works well, right? So core is working, browsing is working, right? And the cell tower is going to send broadcast messages every millisecond, right? And attacker will inject message, like using signal overshadowing. And that message say, there is one message called access barring, meaning that the cell tower says, oh, I'm tired, please do not send the message. And when you send the access barring here, actually the paging messages, these paging messages are injected through SIGOver, right? Because there is no authentication, I mean, you can inject it if the timing is right. So it says, please do not connect me, right? And they turn off the attack. Because, I mean, the cell tower says, I'm tired, do not send me. And even after they turn off the attack, right? They have some timer, and for that time, for 40 minutes, nothing works, right? Until time expires. And this is like, so when we reported this vulnerability to GSMA, oh, this attack, because they know that this attack is possible. I don't know if they knew it. But anyway, when we report this vulnerability to GSMA, their response was actually hilarious. And they say, oh, Yongdae, we will close this case because this attack is academically interesting, but commercially not. So immediately when I received the message, I had a prepared message to them. Then can I open source it? Because you said it's not commercially viable. And it took like 2 weeks before they can answer it. And they say, we never discourage academia to publish open source. But unless you have any very special reason to do it, please don't. Right. So that was actually beginning of my discussion with the GSMA, and I've been having a good relation with them. But anyway, so. And another implementation we did was actually, this is, yeah, I can see. So, and recently we started, because we have the full stateful, we experienced already with the stateful testing. So we were thinking, can we actually move to memory fuzzing, right? So we are developing some memory fuzzing, and see. So as soon as the phone is connected to the network, it's this poor phone. As soon as it is connected to the network, it dies. It's a modem crash, right? Right. And let's, yeah. recently we started the new project with the Korean police. So they say the Korean voice fishers are located usually in China or Philippines, and they are using Simbox to do voice phishing fraud. Okay, and so we got a $6 million project from actually Korean police to handle the Simbox case. So we have probably 2 or 3 or 4 solutions in the proposal. And so, I mean, I just talk about 2 cases. One is, can we fingerprint Simbox from the phone, right? Is Simbox different from when you do RSC attach or NAS attach? Usually phone has to send out its capabilities. And those capabilities are really different from the baseband of the Simbox, because phone manufacturer, if you go to Samsung or Apple, every year they add new features. And every year the standard changes. But in case of actually Simbox, they use actually a very poor baseband. So it's actually very easy to distinguish. And we are checking that fingerprinting Simbox work within the SK Telecom, which is one of the major carrier now. And the second work we do is the physical localization of the Simbox. Or can I find a phone physically if I know the phone number? So this is actually a very, very interesting project. Now my students will come to talk about LTE sniffer as well as the phone localization.
So hello everyone, this is Taek from KAIST. I'm a PhD student of the Professor Yongdae Kim. So I know my name is very hard to pronounce to you guys. So you can just call me Taek, okay? So, right, very good. So from now on, I will introduce the 2 recent researches with a technical view. First one is LTE sniffer. We developed LTE sniffer to provide advanced LTE channel eavesdropper with several security APIs. Our LTE sniffer adopts behaviors of both UE and base station in downlink and uplink channels. We also applied 3 new approaches to our design for effective LTE eavesdropping. Based on them, we were able to improve the sniffing performance compared to other sniffers. LTE sniffer is implemented on the top of Falcon with the help of the srsRAN library. So this design and implementation enables LTE sniffer to support various functions. So in particular, LTE sniffer supports decoding of uplink and downlink control and data channels. In downlink, LTE sniffer can decode PDCCH and PDSCH channels. In uplink, it can decode PUSCH channel. And LTE sniffer supports up to 256 QAM in both channels. For further analysis, LTE sniffer can store decoded package in PK files. In addition, LTE sniffer supports a security API with 3 functions: RNTI and TMG mapping, image collecting, and UE capability profiling. And now we have released the LTE sniffer code on GitHub project. So notably, LTE sniffer GitHub project achieved more than 1K stars. So then you can scan the QR code on the right-hand side to access our repository. Let me show you a demo video. We used the 2 LTE sniffers. We made a phone call to the victim UE every 15 seconds. Then you can see the same TMG appears every 15 seconds, like this. And you can see another another TMZ from other users. And then we can find out the TMZ of the victim. Now we can use it to use map with the RNTI of the victim. Like this. And then using that RNTI value, we can sniff the uplink traffic of the victim. Right? So using this sniffer, the unprivileged attacker can trace the victim UE's physical location by eavesdropping downlink and uplink channels. But to trace the victim's physical location, the attacker should obtain the victim's RNTI first. The RNTI is required to identify the uplink resource allocation of the victim. After that, the attacker can monitor the victim signal on the victim's uplink resources. And finally, the attacker can, using the victim signal, the attacker can find out the direction of signal source and then determine the physical location of the victim by rotating the directional antenna. However, in this procedure, there are several challenges. This is because the unprivileged attacker has no permission to access or control to UEM base station. The first challenge is RNTI is temporary radio identifier. So RNTI changes every disconnections. So for example, when the victim UE is quits the voice call during the location tracking, the RNTI will be expired in about 15 seconds. At this time, the attacker should obtain the RNTI again for location tracking. And second one is when the victim UE is not using LTE service such as voice call, the uplink traffic of the victim is not guaranteed to attacker. At this time, the attacker cannot eavesdrop the uplink signal of the victim. And finally, if the victim UE transmits its uplink signal with very low power, the attacker cannot detect the victim's uplink signal. For example, if the victim UE is located close to the base station, the victim UE will transmit its uplink signal very low power. This is because of better channel quality. So these challenges make the attacker very hard to trace the victim's location. To address these solutions, we introduced two attacks. First, the attacker can force the victim UE to generate uplink traffic continuously. This attack is called scheduling manipulation attack. This attack exploits the scheduling mechanism in LTE network. By doing this, the attacker can maintain the radio connection of the victim and fix the victim's RNTI continuously. And then the attacker can force the target victim UE to increase their uplink transmission power by exploiting power control mechanism in LTE. This attack is called power boosting attack. With this attack, the attacker can overcome the above challenges and then find out the physical location of the victim. We implemented these attacks using srsRAN and USLP and exploiting vulnerabilities of LTE network protocols. So let me show you a demo video. We used the Galaxy S10 to show the attacks. In normal case of the LTE network connection, the victim UE transmits uplink signal lower than 10 dBm. And then radio connection will be expired after 20 seconds. Like this. Then in attack case, can I skip the video? Okay, this is very long. So in attack case, doing the scheduling manipulation attack and power boosting attack. Wait a second, sorry. Because we have to show the radio connection is maintaining, right? So radio connection is maintained even after 20 seconds. And you can see the transmission power increase up to the maximum level, 23 dBm. Like this. So, okay. So as Yongdae mentioned, we are cooperating with the Korean police agency to defeat the voice phishing fraud. The Korean police agency aimed to trace and seize illegal devices used in the voice phishing fraud. So to help the Korean police's needs, we developed vehicle-mounted location tracker using LT sniffer and previous attacks. Using this speaker, the attacker can force the illegal device to continuously generate uplink traffic and force them to increase their uplink transmission power. So, okay, 됐습니다. So, Yongdae will continue the presentation.
So, do you think this attack sounds dangerous? Right? It's a physical tracking, right? So when we report these two vulnerabilities to GSMA, there's another interesting experience. And those are actually vulnerability in the MAC layer, so layer 2. And as you know, if you know the security of Cellular, there is no authentication whatsoever in layer 2. Okay? And we can control the power of the victim phone. And also we can make the victim phone keep sending uplink signal, right? Only by using the layer 2 protocols. And so we report it to GSMA, they say, both attacks sounds very, very dangerous. And the whole scenario is actually very dangerous. But because this is layer 2, we are not going to add any security. That's it. So that's what I mean by if they refuse to secure it, what should I do? They're not going to do it. Anyway. So we have actually many future work to do. So as I told you, there are many specification vulnerability that have not been patched in 5G. Okay? And I really want to patch it. But I mean, one way to do it is actually open sourcing attacks. So it's called Metasploit. If you know the Metasploit in security domain, one can think about implementing Cellular Metasploit, or I don't know whether, I mean, anybody can make it open source, but when you think about implementing intrusion detection system, you need packets or you need traffic, right? But where is it? There is no attacks other than some of our attacks. And because there are, I mean, I think in the morning, the NSF doctor talked about private 5G requirements. Actually, I have already visited, I have talked to several Korean companies who deployed private 5G. And there are 40 deployments cases in Korea already, private 5G. Okay? And they don't know what kind of insecurities exist in 5G design. And they just blindly using it. So, yeah. So probably we need to investigate whether those standard attacks can be launched against private 5G application, as well as then can we secure some of those private 5G designs, right? Do we have the same requirement? Do we need to support the same requirement as the actually 5G standard? Or because it's a private 5G, we may actually improve security in the design. Or eventually, can we fix those vulnerabilities in 6G is still a question, right? And lastly, if standard decide not to patch design, then location tracking is a good application for military purpose or police purpose. Can we actually develop applications exploiting insecurities? What kind of clever ideas exist, right? This is a perfectly zero-day vulnerability that is usable for next 20 years. Right now, that location tracking vulnerability, that vulnerability will not be patched in 5G. That means for 20 years, it's going to be unpatched. It's a 0-day. It's ridiculous, right? And we want to do 5G OTA, uplink, downlink testing, and implementation vulnerabilities, as well as the memory fuzzers. And we want to implement 5G sniffer, 5G SIG-over, 5G fake base station, and MITM. The previous attack I have shown is all for LTE, but not for 5G. And here's reason why we couldn't. So we've been using only srsRAN for analyzing, testing, and improving security of LTE, uplink, downlink, fuzzing, attack demo, tool development, commercial system, and it has been the de facto enabler for LTE security. But for 5G, we are not using srsRAN. I came here to bashing because physical layer features are limited, right? Only 15 in the UE side. SRS UE currently only support FDD in 5G SA mode, but Korean KT network supports 5G TDD, SA mode, and 30 kilohertz SCS. So I came I came here to say that please support TDD, SA mode, and 30 kilohertz. Otherwise, we cannot do this kind of research anymore. Thank you very much.
Thanks, Yongdae. I think the message was loud and clear. Any questions for Professor Kim? Yep. Just for the recording, if you don't mind.
Oh, sure.
Thanks very much.
Have you found any alternatives to srsRAN for the type of testing you're trying to do?
So as I said in the beginning, SRS code is really, really good. And there is nothing comparable, I think, compared to SRS. But if these hardware features are not supported, then we probably right now think about OpenAI. What did we want to use? Oh, yeah, OAI right now. But I really wish the SRS can provide it. And so we actually had discussion about it. So money is not a problem. They need manpower who will do it. So we were discussing about sending one of my students there, Barcelona. Anyway, yeah.
Any other questions? Okay, let's thank our speaker.
All right.